Good morning, students. So we were talking about the pairwise comparisons. That is when you conduct the complete randomized design and when you use the Anova table to do your analysis, we can first find out whether all the means are equal or there is any difference between means. So if there is any difference between means, so what you can do is we can find out what are the different pairs and what are the equal pairs. So for that, we have to conduct the pairwise comparisons. So in the previous lecture, we discussed one method, that is using the Duncan's table, how to conduct the pairwise comparisons. And there's another method called the least significant difference test. So today we are going to discuss this least significant difference test. We can use this one also to compare whether the treatment mean is different or not. So in this case, actually, what we do is when you're writing the hypothesis. Now in Duncan's test, we use the treatment mean to write down the hypothesis. But here we are using the treatment effect to write down the hypothesis. That is, now for an example, let's say you have two treatments in your CRD, treatment I and treatment J. In that case, what you can do is you can write down the hypothesis, that is H note, whether the two treatment effects are equal, and H1, whether the two treatment effects are not equal. Now in this method, it's like you can take two treatments at a time and then compare the two treatments. You can see whether there is any difference or not by taking two treatments at a time. So in this case, since we are taking the treatment to write down the hypothesis, now if you can remember the treatment effect model, it looks like this. So that is you have the mean, you have the treatment effect, and you have the error term. So in that case, if you just take the expected value of this one, you will see it's equal to mu plus tau I. And because we know when you take mu, it's a constant, so the expected value is equal to mu. And when you take tau I, the expected value of tau I, that is equal to tau I. But when you take the expected value of the error term, we know with the assumptions, the error term's expected value should be equal to 0. So you can see the expected value is equal to mu plus tau I. So when it comes to the two different treatments, let's say x bar I dot and x bar j dot, then when it comes to two different treatments, you can write for the treatment I, the expected value is mu plus tau I, and for the treatment J, the expected value is mu plus tau J. So you can see mu will cancel out, and when you take the difference between the treatment effects, it's equal to the expectation. Likewise, we can show when you take the variance is equal to sigma squared times 1 over ni plus 1 over nj. So we know the mean value, we know the variance. In that case, we can, if you take the test statistic as the difference between these two treatment means, we can convert that into a T distribution, that is by you can subtract the mean and divide it by the standard deviation. So this is the variance value. You can take the square root of this to take the standard deviation. And in this case, we know the sigma squared, that's the variance. So what you can do is you can replace the variance by the sample mean value, and for the sample, the sample variance value, you can replace the population variance by the sample variance. And in that case, for the sample variance, you can use the mean square error as a good estimator for the sample variance. So you can replace SP squared value by mean square error value. So actually this test statistic is having a T distribution with degrees of freedom n minus k. That is, n is the total number of observations you have and k is the number of treatments you have. So what you have to do is, if you are comparing any two different treatments, so first you have to find their treatment means, and you have to calculate the difference between the treatment means and take the absolute value. And then you have to calculate this test statistic. If the calculated absolute value is greater than the test statistic, what you can do is, we can just reject H naught, right? And then that is the difference. If you are rejecting H naught, that is, you are rejecting this hypothesis. So you can get into the conclusion that the two treatment effects are not equal. So if you look at this example, so in this case, this is actually, if we use the previous example that we have been discussing, in that case, we have already constructed the Anova table. So we found that mean square error is 8.06. So let's say we want to compare the first and the second treatment in the example. So when you write your hypothesis, you have to write down H naught as τ1 equal to 2 and H1 is τ1 not equal to 2. So first thing you can do is, you can calculate your test statistic. And in that case, when you calculate this one, so you can write T, a capital N is, we have all together 25 observations and we have 5 treatments. So that is 25 minus 5, alpha is 0.05. And then you can take the mean SP squared, you can replace by the mean square error, that is 8.06. And in that example, we have 5 observations in every treatment. So that is 1/5 plus 1/5. So when you solve this, when you simplify this one, you will get the least significant difference is equal to 3.7. And then when you take the treatment mean of the first treatment and the second treatment, and if you take the difference, that is 9.8 minus 15.4. And when you take the absolute value, that is equal to 5.6. So in that case, when you compare this difference between the two treatment means and this calculated value, you can see the difference between the two treatment means that is larger than this LSD value. So in that case, you can reject H naught at 0.05 level of significance. So that is, the conclusion is the two treatment effects are not equal. So likewise, you can take any two treatment means and then you can compare and get into the conclusion whether the treatment means are equal or not. So you can use the Duncan's test, or else you can use this method to compare the pairwise comparisons and get into the conclusion about the treatments. So here is another example. it's about fertilizer levels. You can see there are 6 different fertilizer levels. So the levels are denoted as 0 and 40, 80, 120, 160, and 200. And under each fertilizer level, we are interested about the yield that you can gain. So we want to check when you are changing the fertilizer level, whether there are any difference in the yield. So for that, what you can do is, now since the fertilizer level is your treatment, first you can construct the Anova table. And when you construct the Anova table, you have to check whether these treatment are all equal, whether they're having the same effect or not. So if they're having the same effect, no problem, you can stop your analysis. But if there is a significant difference, then you have to do the pairwise comparisons, right? So you can just conduct this Duncan test or the LSD test and see what are the differences in the fertilizer levels, right? So I'm not going to explain it now here. So in this case, if you look at this one, now when we want to find out confidence intervals, we can actually use for any given treatment mean, we can find a confidence interval. So if you take the treatment, if you take I treatment, when you take the treatment mean as mu I, you can just construct the confidence interval using this. That is, first you have to take the treatment mean plus or minus. You have to take the t distribution table value, and then you have mean square error divided by ni. So this will give you a confidence interval for any treatment level. So let's see, here you have to calculate the 95% confidence limits for the treatment means in the above example. That is, when you take this fertilizer level example, let's see how to calculate 95% confidence interval. So let me share you the Excel. Okay, so in this case, can you all see the Excel?
Yes, madam.
So, okay, now here, this is our data set. So we have the different type of fertilizer levels. Here, these are the fertilizer levels. So there are the treatments. So you have 6 different treatments. So I have done the calculation, and here I have constructed the Anova table. This is the Anova table. So just take the data set and just construct the Anova table and see whether you get the same values, right? So I will show you now in this case, when you take the Anova table, and if you here you can see the F value is 68.98. So actually this is a big F value. So when you compare this with the table value, you will see this calculated F value is greater than the table value. So you can reject H naught. That is, there is a significant difference between the treatments. So then we have to find what are the differences. So for that, you can conduct the LSD test, or you can conduct the Duncan's test. Now here what I'm going to show you is how to construct the confidence intervals. So when it comes to confidence intervals, so we have 6 different treatments, 0, 40, 80, 120, 160, and 200. These are the 6 different treatments. So in this case, I have calculated the treatment means. Here, these are the treatment means that I have calculated. How you calculate the treatment means? First, you have to take the total of the observations under each treatment. So here, if you take the total of these set of observations, it's adding up to 20.075. So under each treatment, you have 5 observations. So I have divided 20.075 by 5, and then I have calculated the mean value for treatment, the first treatment, that is level 0, as in this example, that is 4.015. Likewise, for this treatment level, for the second one, the mean value is 5.2284. For this one, 5.81. Likewise, I have calculated the mean value. So in this case, so I'll just take the mean values. And first you can I'll just put the mean values here: 4.015, 5.2284, and then you have 5.8146, 6.9928, 7.2712, 6.9896. So we have the treatment mean values. So the next thing is, when you take the confidence interval, you can see first you have to calculate the treatment mean plus or minus table value. You have to read from the T table, and then mean square error divided by the sample size of each treatment, and you have to take the square root. So this part we can do the calculation. That is, you have to take the square root of mean square error value, and then you have to divide it by the sample size of each treatment, right? So in this case, if you take this mean square error value, if you look at the Anova table, you can see here, when you look at the Anova table, the mean square error value is equal to 0.117917. So that is, if you are planning to construct the confidence interval, the first thing that you have to do is you have to construct the Anova table to find out the mean square error. Okay. Not actually the full Anova table. You can find the SSE, and you can divide it by the respective degrees of freedom. You have to find, then you can find the MSE value. So that is the first thing you have to do if you are planning to construct the Anova confidence interval. So in this case, we have already constructed the confidence, the MSE value, the Anova table. So I'm going to take the MSE value, and then I'm going to divide it by 5, because under each treatment we have 5 observations as for this example, and then you have to take the square root value of this. You have to take the square root value of this. So the mean square error, that is same for all the observations. So I'm going to lock that value. Okay, so I'm going to do the calculations here like this. So you can see for each and every treatment, you get the same value for this, because mean square error is the same and the sample size under each treatment is the same. So you get the same value when you take the square root for MSE divided by NI. And the next thing is, now we have to find the table value. So the table value for T n minus k and alpha over 2. So alpha is, since we are constructing the 95% confidence intervals, you can take alpha as 0.05, and then when you take n minus k value, so n is 25 minus k. So k is 5, that is T20. So that you have to find the table value. So if you find the table value, you will see when degrees of freedom is equal to 20 and when alpha is equal to 0.05, you will see the table value is equal to 2.086. If you read the T table, it's 2.086, the table value, right? So here I'll just put the table value, that is 2.086. So the table value is the same for all the treatment levels. So now we can construct the upper bound and the lower bound for each treatment confidence interval. So if you take the first treatment, that is, you have to calculate the upper bound of the confidence interval. What you have to do, you have to take the mean value and then you have to add the multiplication of the square root of mean square error divided by the treatment sample size and into the table value of the T distribution. So this will give you the upper bound for your confidence interval. And when it comes to the lower bound, what you have to do, you have to take the sample mean, subtract the multiplication of these two terms. Right? So then likewise, we can construct the confidence intervals. Here you can see the 95% confidence intervals for each treatment. Okay, so this is how we construct the 95% confidence intervals for each treatment. Okay, so do you have any questions regarding this calculation of the confidence intervals? So I'm going to share the note again. Okay, so if you have no questions regarding the confidence intervals, so in this case, we can, there's another test. Now we can use the Duncan's test, we can use the LST test to see whether there is any difference between the treatment means, and you can use this formula to construct 95% confidence interval for the treatment means. Also, in some conditions, in some examples, in some problems, sometimes when you check the treatment groups, there is also a control group. For an example, now if you look at this one, the fertilizer example, here we have six different treatment levels. Now in these six different treatment levels, if you take the first treatment level, that is level 0, in this case, if you keep that level as the control group, what you want to do is always we want to compare other treatments with this control group, right? So we want to compare the effect of the other fertilizers with this first treatment group. So this one we call as the control group. So sometimes in some problems that we come across, especially in real life situations, you will see control groups are there when you are constructing CRDs. So in that case, we have to compare all the other treatments with the control group. So if that is your case, what you can do is you can what you can do is you can use this test in order to compare a given treatment with the control group. That is, for an example, let's say treatment K is your control treatment, and in that case, if we have another treatment called treatment I, and if you want to compare the treatment I with the control treatment K, so you can write down the hypothesis as mu I equal mu K and H1 as mu I not equal mu K. So you can compare any mu I with the control. So mu I can go up from 1 to up to K minus 1 if you take K treatment as the control group. So in this case, we have a procedure called, we have a table called Donet Table. So from the Donet Table, we can read the values, and using this test statistic, we can actually compare a control group and another treatment, and whether there is any difference between the control group and the other treatment. So if you look at this one, you can see first you have to obtain the mean square error from the Anova table, and then Ni means the number of observations you have under ith treatment, and Nk is the number of observations you have under the control group, and alpha level is the significance level, and this one dk minus 1 comma n minus k, that is you have to read from the Donet table, and then here you have to take the difference between the absolute difference between the treatment mean that you are comparing with the control group, right? So in this case, if let's say the example here, they're asking us to compare the treatment means of the above example with control treatment 0 fertilizer level. So in that case, what you have to do is when you're writing the hypothesis, so 0 you can take as the control group. So what you can do is when you write H note, you can write in this case, let's say you are going to compare the first, here the 0 level is the control one. Let's say you are going to compare with this level. So that is 40. So the treatment level 40. So that is you can take mu 40 equal mu 0. Or else you can write your null hypothesis as mu 40 not equal mu 0. So this will be the hypothesis that you are going to test, right? You can test whether mu 40 is equal to the control group, or there is any difference between these two treatments, that is the control group and the level 40. So for that, you can use this Donet table calculation. So I will show you how to do that. Okay, so here now we are going to do the calculations when we have a control group. So let's see how to do the calculation. So our control group is always 0, and here we have already constructed the mean values. So I'm going to just copy and paste it here. Okay, so for each So what we are going to do is we are going to do comparisons with the control group. So in this case, 0 level is our control level, and we have already constructed the mean values. So let's first, what you can do is you can check the difference between your control and the mean values of each treatment. So here I'm going to calculate the difference. So if you take this treatment level, the mean value is 5.2284, and here the control mean value is 4.015. So this is the difference. And likewise, you can calculate the difference here. That is, the mean value of this treatment level is 5.81, and the control mean is this. So the mean value for this one is 6.99, and for the control is this. And the mean value for this one is 7.27, and control is this. For the last treatment, mean value is 6.98, and for the control this. So now we have, since all are positive values, it's the same when you take the absolute difference as well. So these are the absolute differences between the treatment that we are interested and the control group. So now we have to calculate this one, that is the square root of mean square error into 1 over ni plus 1 over nk. Now, based on this example, you can see for each treatment level, you have the same number of replicates. You have 5 observations. So that is 1 over ni is 1 over 5 plus 1 over nk is again 1 over 5. So that would be equal to 2 over 5. So in this case, what you can do is you can calculate the square root of mean square error into 2 over 5. This is what you have to do. So let's do the calculation. You have to take the square root of the mean square error is equal to this value, which is coming from the Anova table, into 2 over 5. And this here. So the Anova table value, that is a constant. So I'm going to lock it up. Okay. So now we have to table, now we have this term, we have calculated the square root term, and we have calculated this difference between the control group mean and the other treatment means. And now another term is left, that is, we have to read from the Donet table. So you can see you have here as the degrees of freedom, you have k minus 1 and n minus k. So based on this example, altogether you have 30 observations and you have 6 treatments, right? So 30 minus 6, it would be 24, and 6 minus 1, it would be equal to 5. So that value you have to read from the Donet table. Now I will show you the Donet table. Give me a second, I'll open the Donet table and show you. So here, Right, here we go. Okay, so I hope you can see it now. So this is the critical values from the Donet test. So you can see you have here number of groups including the control group, and here you have the n value. So in this case, you have the alpha value as well. So what you have to do is, based on our example n minus k value, you have to read as the n value. So in our example, n minus k value is 24. We have capital N is 30 and we have k is 6, six number of treatments. So 30 minus 6 is 24. So we have to read 24 from this column. And then k minus 1. Here they are giving the number of groups including the control group. So but we want to take the number of treatments and reduce the control group and find the value from the table. So k minus 1, since we have k number 6 number of treatments, k is equal to 6. 6 minus 1 is 5. So here we have to read 5 from this column. So that would be 1, 2, 3, 4, fourth column. So let's see. So 1, 2, 3, 4. So alpha is 0.05. So in that case, from the Donet table, we can get the table value as 2.61. So that's how you read the table value from this one. So let's go back to the calculations. So from the Donet table, we have 2.61. So the D value, that is 2.61 from the table. Now we have all the values. So we can simplify. That is, you have to take the Donet table value and multiply the square root term. So I'm going to do the multiplication. Let's take the product of these two terms. Right. Now in this case, so let's check. This is the value that you have to compare with the absolute difference of the treatment means. Now, if you check these absolute differences, you can see 1.21, and this one you can see here it's great. When you take this one, it's the difference is less than this calculated value. Again, here the difference is less than the calculated value. Right, and when you compare all the differences, you can see the differences are less than the calculated value. So in that case, we cannot reject H naught. So that is when you take the control group and when you compare the means, even though from the Anova table there is a significant difference, we cannot conclude there is a significant difference with the treatment means, right? So like this, you can conduct the comparisons when you have a control group using the Donet table. And there is another thing I want to share with y'all. So when you're doing the calculations for this, for these complete randomized designs, right? So if you can remember the cotton percentage example that we discussed earlier, and also for this fertilizer example. So when you want to construct the Anova table, you have to use those formulas and do all the calculations. But in that case, if you want, you can code all the data and do your calculation. Coding means what you can do is, if you look at the cotton percentage example, there we had 5 different treatment levels. So in that case, you have observations. Let's say from each and every observation, you can just subtract or you can add a constant value. So let's say you're going to subtract 15 from each and every observation, right? So from this one, you can subtract 15. Likewise, now then you will get some values. In that case, some of the observations will become 0, because if you look at this table, you can see here it's 0, because here the actual observation was equal to 15. So when you subtract 15, this observation became 0, right? Here it was 7. So when you subtract 15, it became -8. So when you subtract 15, so it should not, like 15 is not a must. You can take any value as you like. So after you subtract 15 from each and every observation, then you get some of these values. So then what you can do is, you can do the same calculation for these coded values. Then you will see you get the same results, right? You get the same results for the treatment sum of square, the total sum of square. You can get the same conclusion. So you get the same Anova table. So why we are doing the codings, that is, now let's say you have numbers in thousands. So if you just subtract 1000, and then if you can reduce the numbers into a smaller value, so the calculation would be much easier. That's why we are doing that. So but you get the same answer, so no problem. So if you like to code your data and do the calculation, that would be fine. Okay, any questions up to that point? If you have any questions, you can raise. Okay, so if you have no questions, what I'm going to do is, I will show you how to do these multiple comparisons using R. Okay, I'll show you how to do multiple comparisons using R. So let's take the fertilizer example. Now, the first thing that you have to do is, you have to save your data set in a CSV file and import your data set to R. So I have done that part. This is our data set. So you have 6 different treatment levels. So with the earlier example, I have explained you how to save your CSV file and how to import that to your to R to do your analysis. So that is the first thing you have to do. You have to import your data set to R. So I have done that part. And then if you are planning to do the multiple comparisons, in that case, what you have to do is, first, you have to take your data set, and then what you have to do is, you have to put all the treatment levels into one column and all the observations of the treatments into another column, and arrange your data set. That is the first thing that you have to do. So what I'm going to do is, I'm going to put all these observations into one column and their respective treatments. Let's say I'm going to code them as item 1, 2, 3, 4, 5, and 6 into another column. So to do that, first I'm going to use, let's say, in order to concatenate the rows and put them into one column, I'm going to, just as we used in the previous example, in the last lecture, I'm going to concatenate the rows like this as dot matrix. The name of my data set is my data. So you can just call R and see. Now here the first row have been concatenated and then you have the second row like that. So now I want to tell this first observation is coming from the treatment 1, second observation is coming from the treatment 2, likewise, right? So to do that, what I'm going to do is I'm going to give the factor names to this one. So that is so let's give the factor names as item 1, item 2, and item 3, and item 4, and 5, and 6. So if you just call F and C, you have item 1, 2, 3, 4, 5, and 6. And then what I'm going to do is, let's see. Now, in this case, if you take K, the number of treatments, the K value is equal to 6. We have 6 different treatments. And when you take the number of replicates, N value is equal to 5. So when I model this, what I can do is here, I can use the function GL as we used earlier. And then you have to give the number of treatments, and starting from 1, you have to go up to N into K and use these factors to give the labels for each and every observation. So if you just call TM, you can see here for the first row observations, they have given item 1, 2, 3, 4, 5, and 6. Then again, they have started from item 2, 3, 4, 5, and 6. Likewise, you can see what has happened here. So now if I want, I can run the Anova table. So that is, I'm going to give a variable name. I'm going to use the built-in function Anova. So by now you know how to run the CRD in R. So that is, first I have to give the concatenate observations and then these labels. Right, so if you take summary of this AV, here you get the Anova table. You can see when you look at the Anova table, the p-value is significant. That is, you can reject H node. That is, there is significant difference between the treatment means. So in this case, in order to check the pairwise comparisons, in order to check what are the mean levels where you can see a difference. So in that case, first you have to put this concatenate row and these labels into 2 columns. So what I'm going to do is I'm going to use a data frame. Let's say my data frame, and then I'm going to put these 2 columns to that data frame. So to do that, I'm going to use the built-in function data.frame, and I'm going to put R and the TM column to my data frame. So I'm going to just see what has happened here. So you will see now I have coded the first here. This item is coming from item 1. This observation is coming from the treatment 1. This observation treatment 2. Likewise, now I have nicely coded all the values. So now to do the pairwise comparisons, there is a test. There is a built-in function called pairwise.t.test in R. So that is pairwise.t.test in R. So here, as the arguments, what you have to do is, here you have to first give the observations. So in here, my observations are in my data frame. Here, the first observation, the observations are coming from the column R, and then you have to give their labels. So they are in my data frame with the dollar mark. The label column is TM. You can see when you do this pairwise comparisons, you will get an output like this. So that is when they are showing you the p-value. So that is when you compare item 1 with item 2, the p-value is 6.7 to power 6.7 into 10 to power minus 5. So that is, it's a very small value. So in this case, you can see when you take that one, that is, you can reject H node. So that is, there is a difference between item 1 and item 2. You can reject H node. But if you look at something like this, when you take the p-value of item 4 and item 6, in this case, it's 0.99. So that is, it's greater than 0.05, our significance level. So you cannot reject H node. So if you cannot reject H node, you have to come to the conclusion that the two treatments, that is treatment 4 and 6, are the same. So likewise, you can conduct the pairwise comparisons using R. So this is not the only method, right? So especially when you are learning R, the methods that I'm teaching, they are not the only methods you have. So it's for you, up to you to search and learn. So I'm giving you the basics so you can see what are the functions you have and what are the other methods, what are the functions for the testings you have. So it's very easy to use R because all the codings are available on the internet. So you can just search and try by yourself. Okay, any questions up to that point? So I have to give you a message. If you go to the Cal page of statistical models, you will see I have uploaded 2 questionnaires, that is for the teach evaluation and course evaluation. Please fill those 2 questionnaires by Monday. So I can get your evaluation for the course. That is important to do further improvements for the next batch. So please fill it out. And also I'll be uploading a tutorial. So you have to do the tutorial and submit. I'll take marks from that, and the tutorial will be discussed on Tuesday. Any questions? Okay, then if you have no questions, I'm going to stop from this point. So thank you very much for coming to the session, and have a nice day.